Hello everyone, welcome to episode 7 of Senseicolonelmathematics, the Differential Equations and Linear Algebra series. Today we're going to be covering judicious guessing. That sounds a little weird, but you'll see why we're guessing soon enough. So again, here's our non-homogeneous equation, except you can see that it has constant coefficients here. A lot of the solutions that we're going to be looking at in this video are going to be dealing with what we looked at in our, I think last to last episode, where we looked at the linear equation with constant coefficients, or that could have been last episode, I can't remember, but let's get right into it. So the thing is that judicious guessing works by basically we're going to be looking at multiple different cases for what g of t actually is, and from those we are going to kind of build off on what we learned in the recent episode, and we're going to hammer things down. So here is our first example of g of t, just a polynomial to the nth degree. Nothing too crazy, right? But so what we're going to do is we're going to make an operator, a solution to this right here, that makes this into a polynomial that's equal to this. How are we going to do that? I feel like whatever we put in there, which is this right here, this is our solution right now, right? My candidate for the solution. Whatever we're gonna put in here is going to get mutilated by all the derivatives and all that stuff, and we're adding it all together. How is it going to equal this? Trust me. So let's set this equal to, let's plug this into the derivative really quick and see what we get. This is some crazy algebra. You guys don't have to write this down if you guys are writing anything down. But yeah, here is like us plugging it into the derivative. So like it's nothing crazy, just power rule, but really intense power rule, which is where we get all of this stuff from. And then so it gets into this, and then we can simplify it into this. All right, so yeah. So this is the equation that we left off on the last slide, and this is supposed to equal this. The thing is that it doesn't really equal this, right? But the thing is that we need to remember that this is a polynomial to the nth degree. This is also a polynomial to the same nth degree, all right? So the thing is that although it doesn't look exactly equal, they are equal, all right? And so this actually is perfect for us because now we found a way to get the left side of our differential equation equal to the right side by just plugging in an operator. We don't need to, we did all the hard work already, all right? So yeah, the issue is the thing is that sometimes this constant right here could equal 0, all right? And so what that does is that, here, wait 1 second. So this is what we have so far. This is our polynomial on the right side, and this is the terms on the left side after we plug in our candidate equation, or our candidate solution that I proposed earlier, which is just another polynomial, into the operator and do all the double derivatives and all that fancy stuff. So this is all equal right here. The issue that happens is that whenever this constant is equal to 0, it kind of breaks everything, and all of a sudden you don't have a polynomial on the left side. You don't have a polynomial to the nth degree anymore. It's to the n minus 1th degree, and so that's bad because then it's not equal to the right side anymore. And so you need to take precautions against that by basically, okay, so this is what happens when we have all of our constants as, like, non-zero values. All right, so this is, we can already say that this is our solution right here, but here's what we do. So this is what happens when c is equal to 0, right? So we have everything on the left side. You guys can plug the things back into the operator if you want to, but then you'll notice that we actually lose a degree on the left side. So what we do to combat that is we just add another t. That's it. It's that easy. And so then that gives us the extra degree that we need on the left side for the things to be equal. So what if we're also missing our constant b? That's also equal to 0. B and c are equal to 0. Then we're just left with this, and so then it's supposed to equal this, right? But these are not equal to each other. But we can know what the solution is by simply taking the double integral of both sides and then dividing the whole thing by this constant a right here, and then we have this. Guys, I'm not gonna lie, the content in this episode is not very difficult, but it was a pain to type all of this out. But yeah, nothing too crazy here. Oh, this does look a little crazy. I take that back. But you don't need to know this, memorize this either, because we can just do the same thing that we did for the last one, except add another t there, just to compensate for the degree loss. So yeah, this is it. If your b and c are gone, then it's this right here. This is going to be your particular solution. If your c is gone, this is going to be your particular solution. And if all your constants are not 0, then this is going to be your particular solution. So if you guys want to see a bit of this in action, let me show you an example right now. So here's our equation right here. And so remember, this is our polynomial on the right side to the nth degree. In this case, it's the second degree. So our candidate solution is also going to be to the second degree. All right. So let's plug it into the operator. This is what we've got right here. This is the, all the second derivative, first derivative, and all that just added together. And so then we can reorganize it into this. And so this is our polynomial to our degrees. This is a proper polynomial. Our c isn't equal to 0. So yeah, everything's going great. So now we need to figure out how can we choose these constants, these big z's, in order so that this actually is fulfilled right here. So basically, this is our 0th degree term right here, which, look, there is no 0th degree term here. So this has to equal 0, all right? And so this is our first degree term right here, like t to the 1. There's no first degree term here, so this also has to equal 0. And this is our second degree term, and there is a second degree term here, and so for this to equal that, our big Z has to equal 1. All right, so this is what we are going to use to find our constants. All right, so yeah, so here's what we're going to use to find our constants. So we already know our big Z of 2, right? And so if we know that big Z of 2 is equal to 1, then this is equal to 2. What plus 2 is going to equal 0, negative 2. So our big Z of 1 is equal to negative 2, right? And then this right here is going to equal 2 because it's 2 times 1. And then this is just going to equal negative 2, which cancels out, which gives us 0 on this side. So what plus 0 equals 0? 0. So our big Z of 0 is equal to 0. All right. So then here is, remember, this is the original particular solution that I posited earlier. We know what these big Z's are, so this is going to be 0, this is going to be negative 2, and this is going to be 1. And so this is our particular solution here. If we were to get a general solution, it would look like, the two linearly independent solutions for the homogeneous part of the equation, aka the left part, plus this whole thing right here. So yeah, nothing too crazy. And so, yeah. Oh, that's some weird transition right there. But yeah, here's our constants. So the next thing we're going to look at is a similar thing, but instead of just a polynomial to the nth degree on the right side, we're going to have a polynomial to the nth degree on the right side times e to the alpha t. All right, so what we're going to do is we're actually going to make what we plug into the operator e to the alpha t times a mystery function called v of t. All right, so here are the first and second derivatives, and so here's us plugging and chugging into the operator. And so yeah, we are trying to get this to equal this, right? So yeah, that's what we have right here. We can divide both sides by this, and then we're just left with this. So yeah. Oh yeah, so basically what the rest of it was showing was not really that, this wasn't really leading up to this, but it was leading up to this right here. All right, so what this right here is saying is, so basically what this shows us is what kind of like e to the alpha t values can we actually use, and how can we, why does this happen right here? So what happens is that, so imagine that all of this is intact, then this right here is going to be a perfect solution to all of this, right? But the issue is that if e to the alpha t is a single root, it's a single root, then what happens is that if like one of the roots is e to the alpha t, then this right here gets destroyed, all right? And so then that's bad, and so remember we lose like another degree in that process, so then we have to reinforce it. And then if e to the alpha t is equal to both roots, then that's bad, because then we lose this, and then we have to double reinforce it, right? And so, yeah, I'm going to show you guys an example, because I feel like that was a lot more confusing. So here's our example right here. We only have one root, so e to the alpha t is going to be both roots. And so, as you may recall from one of the previous episodes, the solution when you have e to the alpha t as one of the only roots, this is your general solution right here, all right? So the thing is that we know that since it's only one root, we're going to be losing two of our big terms in the left-hand side polynomial, so we need to double reinforce it, so we have t squared here times a big z of 0, all right? Here's the derivatives of it, and so here's us plugging and chugging it into the operator. And so then it all simplifies down into this. And so, yeah. So this operator right here is supposed to equal this, and then we can look at this right here, and then simplify it down, and this is what our big z of 0 is going to look like. And so from that, we actually know now that our particular solution is this right here. That did feel kind of simpler than the last one, right? Or I guess simpler in a different way. And so the thing is this is just a particular solution, but we already have our general solution for the homogeneous part of it. So now we can find our general solution for the entire non-homogeneous equation. This is it right here. So now we're going to look at what happens when we have an operator and we multiply it by cosine beta or sine beta. Alright, so first let's get into theory mode really quick. So imagine that we have a solution of this operator down here, this non-homogeneous equation, that is a complex solution. Alright, it's x of t plus an imaginary k of t. Alright, and so equals g of t, and g of t is also equal to g1 of t plus an imaginary g2 of t, because it's a complex solution, right? So the thing is that so when we plug in this operator here, we're obviously going to get this, right? But the thing is that if you break it up into two, if you just do the x of t, you'll just get g1, all right? And then if you plug in k of t, then you're going to get, this is real k of t, by the way, and so then you're going to get real g of 2. But if you make it imaginary, this just becomes imaginary g of 2. But the thing is that it's still a solution. This right here is still a solution, so don't discriminate against the imaginary. All right. So look, we're back here, and so here's our operator, or our solution f of t, combination of solutions f of t. And so here we can actually recall from, I believe, the last episode that this is this. So again, we're just looking at one of the equations that we were looking at in our last little hypothetical scenario where it's e to the alpha t, except it's this. All right, and so yeah, nothing too crazy there. And so the thing is that there's just going to be, depending on what you're looking for, there's going to be a real part of the solution and an imaginary part of the solution. Because if you were to swap this out right here and then distribute here and here, then the thing is, one of the parts of the solution is going to be imaginary, one of the parts of it is going to be real. You know what? Do you guys know what I mean? If you don't, I'm going to show you an example right now. So here's our example right here. And so, just by the way, the roots for this, if we made it into a polynomial, which would become r squared plus 4r, it has two roots, which is positive 2i and negative 2i. So basically this right here, our e to the i2 or e to the 2i, that's one of our roots. So our little hypothetical candidate right here, it's going to be only medium reinforced, if you guys remember what I'm talking about from the last hypothetical. So it's just going to be 2 to the e2it. All right, so here's the thing with the right side of this. We know that this is the imaginary part of this right here. All right, so what we're going to be looking for is the imaginary part of the solution, right? The imaginary solution. Because remember that the solution can be part of a bigger solution. So that's, yeah, so don't get confused when I keep saying solution or parts of solution for the same thing. So yeah, look at this. Here's our hypothetical, the double derivative of the hypothetical. We plug and chug them into the operator, and then so then it reduces down into this right here, and this right here, and then so this is supposed to equal our this right here, right? And so then we get this. Are you guys following? But yeah, this is what happens when we get rid of this 2 right here and then divide everything by 4i, right? So this is what our big z of 0 is going to look like. And so yeah, here's our hypothetical right here, and the thing is that this, remember, this is like the 7th time I've shown this right now in this example, And then, so then here's our hypothetical, but in another line. Another face of our hypothetical, right? Ooh. God. Yeah, and then and then we know what our big zero is, so we can plug this in right here. And remember what we were looking for, since we were looking for, the imaginary part of the solution, right? Because it's the imaginary part of this, right? Imaginary sine 2 of t. We're looking for the imaginary part of the solution. This is our imaginary solution right here, okay? So the thing is, guys, if this said cosine 2 of t, we'd be looking for the real solution, because that's the real part of this. And so this right here is the real solution, all right? So yeah, there we go. Thank you for watching. I hope you enjoyed.